Welcome to this hands-on training on MiniCPM5-1B. MiniCPM5-1B is a compact, 1 billion parameter language model from OpenBMB that is small enough to run on a single consumer graphics card, yet capable enough to reason, write code, and use tools. Over the next half hour, we'll walk the full journey together. First, the core concepts behind the model, then its benchmark results, then a clean installation on an RTX 4090. The key configuration choices, and finally 4 working use cases that you can run yourself. Let's get started. We'll begin with the concepts. The goal here is not to drown you in theory, but to give you just enough of a mental model to use the rest of the training confidently. We'll cover what the model is, how it's built, the 2 ways it can think, how it calls tools, and where it can run. So what exactly is MiniCPM5-1B? It is a dense transformer with roughly 1 billion parameters, designed specifically for on-device and resource-constrained deployment. Think laptops, edge boxes, and single consumer GPUs. Despite that small size, it reaches the open-source state-of-the-art for its class, meaning it outperforms other 1 billion parameter models on average. The clever part is that a single checkpoint behaves as 2 different assistants, a fast, direct responder, and a slower, deliberate reasoner. And because it is so compact, the weights occupy only about 2 gigabytes in bfloat 16, so it loads in about a second and leaves plenty of memory to spare. Under the hood, the architecture is deliberately conventional, and that is a feature, not a limitation. MiniCPM5-1B is a standard Llama for causal language modeling network, which means mainstream inference engines can load it directly, with no custom kernels and no forked model code. It has a hidden size of 1,536 spread across 24 transformer layers. It uses grouped query attention, with 16 query heads sharing just 2 key value heads, which keeps the memory footprint small during generation. And it supports a very long context window of up to 128,000 tokens, drawn from a vocabulary of about 130,000 tokens. Because it is plain Llama, everything you already know about running Llama models applies here. The headline capability is hybrid reasoning. The same weights can operate in 2 distinct modes. In think mode, the model first writes out a visible, step-by-step reasoning block before committing to an answer. This is ideal for math, logic, and multi-step problems. In no-think mode, it skips that deliberation and answers immediately, which is perfect for quick chat and knowledge questions where speed matters. You choose the mode at prompt build time with a single flag called enable_thinking, set to true or false. Alternatively, you can simply append /think or /nothink to the end of your question. No model swapping, no reloading, just 1 flag. MiniCPM5-1B is also genuinely agentic. It can call tools. You describe your tools as standard JSON schemas and pass them to the chat template. When the model decides a tool is needed, it emits a function call as a simple XML tag, naming the function and its parameters. Your application parses that XML, runs the actual Python function, and feeds the result back to the model as a tool message. The model then reads that result and writes the final, natural language answer for the user. This whole loop runs in plain transformers with no server required, and in production, serving engines like sglang can parse those calls for you automatically. Because the model is plain Llama, it runs almost everywhere. For a quick Python script, you use Hugging Face transformers, and that's what we'll do in this training. For high-throughput production serving, you reach for VLLM or sglang. If you're on a CPU, a low VRAM machine, or a laptop, the GGU builds run beautifully under llama.cpp, Llama or LM Studio. And on a Mac, the MLX build gives you native Apple Silicon speed. The repository ships a 1-page cookbook and an agent skill for each of these backends, so whichever route you pick, there is a tested recipe waiting for you. Now that we understand what the model is, let's look at how well it actually performs. Numbers matter, so let's see where MiniCPM5-1B lands against its peers. Here is the central result. Across a broad suite of 7 domains, reasoning, knowledge, code, instruction following, math, logic, and agentic tool use, MiniCPM5-1B reaches an average score of about 42.6. The strongest comparable open-source models in the same 1 billion parameter class average around 35.6. That is a margin of roughly 7 points, which is substantial at this scale. In other words, for its size, this model is at the front of the pack, and it gets there with weights you can download and run on hardware you already own. Averages can hide the interesting story, so let's zoom in. The model's strengths are most visible in 3 areas. First, agentic tool use. It reliably picks the right function and fills in the right arguments. Second, code. It writes programs that actually compile and run correctly the first time. And third, competition-grade math, where it handles multi-step derivations rather than just guessing. Crucially, it delivers all of this while remaining small and fast, which is exactly the combination that makes an on-device model genuinely useful, rather than just impressive on paper. Before we install anything, let's make the central trade-off concrete, because you'll be choosing between these 2 modes constantly. Think mode produces a visible chain of reasoning. It is the right choice for math, logic, and hard multi-step problems, and it earns higher accuracy on tricky tasks, but it spends more tokens and takes more time. No think mode answers immediately in a single pass. It is the right choice for chat and quick factual questions, where it gives you the fewest tokens and the lowest latency for a snappy assistant experience. Same model, same memory. You simply pick the behavior that fits the task. With the concepts and benchmarks behind us, let's get our hands dirty. We'll set up a clean, reproducible environment on an RTX 4090, step by step. Everything here was actually run on the machine, so you can follow along exactly. Step 1 is the environment. We use 2 modern tools together. The first, asdf, pins the exact Python version. Here, Python 3.12, so the setup is reproducible across machines. The second, of, is an extremely fast environment manager that builds the virtual environment from that pinned interpreter. The single command you see creates a .venv folder using the Python that asdf provides. We then check the interpreter version to confirm everything points at Python 3.12.8. This isolated environment keeps the model's dependencies from colliding with anything else on the system. And here is what that looks like in the terminal. You can see asdf reporting the Python 3.12.8 interpreter of creating the virtual environment almost instantly, and the final version check confirming we're on the interpreter we expect. This is the entire foundation, isolated, reproducible, and built in well under a second. From here, every command we run uses this environment's Python explicitly. Step 2 installs the dependencies. The most important pin to remember is that MiniCPM5 requires Hugging Face Transformers version 5.6 or newer. Earlier versions will not load it correctly. Alongside Transformers, we install PyTorch, which brings the CUDA runtime for the GPU, plus Accelerate for device placement, Safe Tensors for fast weight loading, and the Hugging Face Hub client for downloads. On this RTX 4090, OV resolves and installs the whole stack, including the CUDA build of PyTorch, in well under a minute. Notice we pass the venv's Python explicitly, so the packages land in our isolated environment and nowhere else. Step 3 fetches the model weights, a small but important habit. We point the hf_home environment variable at a dedicated cache disk, rather than letting gigabytes pile up on the system drive. Then a single if download command pulls the model from the Hugging Face hub. MiniCPM5-1B is only about 2.1 gigabytes, and it is cached once. Every script afterward loads straight from this cache with no re-download. If you prefer the smaller quantized GGUF or the Apple MLX build, you would simply download those repositories instead. Before loading a large model, it is always worth a 10-second sanity check that PyTorch can actually talk to the GPU. This snippet confirms that QDA is available. That torch sees the RTX 4090 with its compute capability of SIM89 and 24 gigabytes of memory. And most importantly, it runs a small bfloat 16 matrix multiplication on the card to prove the QDA runtime really works end-to-end. If this passes, you know the heavy lifting will succeed. If it fails here, you've caught a driver or install problem before wasting time loading weights. Installation done. Now let's look at configuration, the handful of choices that determine how the model behaves once it's loaded. Get these right and everything just works. Here is the canonical loading pattern, and it's worth reading closely because every use case builds on it. We load the tokenizer and the model from the cached checkpoint, asking for bfloat 16 precision and placing it on the CUDA device. We then build a chat message list and pass it through the tokenizer's applyChat template method. Two details matter for Transformers version 5. First, enable_thinking is where you flip between reasoning and fast mode. Second, you must pass return_dict equals true, and then call generate with double star inputs, because in Transformers 5 the template returns a dictionary rather than a bare tensor. Finally, we decode only the newly generated tokens to get the model's reply. The model ships with recommended sampling settings, and matching the mode to the right temperature makes a real difference in quality. For think mode, set enable thinking to true and use a temperature of 0.9 with top of 0.95. The slightly higher temperature lets the model explore the reasoning space. For no think mode, set enable thinking to false and drop the temperature to 0.7, keeping top at 0.95, which yields tighter, more direct answers. These are sensible starting points. For fully deterministic, repeatable output, useful in tool calling and code generation, you can simply turn sampling off entirely. There is exactly one gotcha you must know about for tool calling, and it will save you a confusing debugging session. The XML tags the model uses for tool calls, function and param, are registered as special tokens in the tokenizer. That means if you decode the output with skip special tokens set to true, as you normally would, those tags are silently deleted and your tool calls vanish into thin air. The fix is simple. When you expect tool calls, decode with skip special tokens set to false, and then manually strip only the chat control markers like the imStart and imEnd tokens. In production, SGLang's built-in MiniCPM5 tool parser does all of this for you automatically. Everything so far has been set up. Now for the fun part, 4 real use cases that put the model through its paces. Each one is a small, self-contained script, and each result you'll see is a genuine capture from running it on the 4090. Use case 1 demonstrates hybrid reasoning directly. We ask a single competition-style question, the sum of all positive divisors of 360, whose answer is 1170, and we run it twice in a loop, flipping the enable thinking flag between false and true. Everything else stays identical. This is the cleanest possible illustration that the mode is just a flag. Same prompt, same model, 2 different minds. Notice we also nudge the temperature higher when thinking is on, following the recommended defaults from the previous slide. And here are the real results. Both modes arrive at the correct answer, 1170. The difference is in how they get there. No think mode produces a concise solution in about 280 tokens and just over 2 seconds. Think mode spends more, around 550 tokens, but it shows a full derivation and even double-checks itself by enumerating all 24 divisors. Throughout, the little model generates at roughly 120 to 145 tokens per second on the 4090. This is the trade-off slide made concrete with actual numbers. Use case 2 runs the full agentic tool calling loop. We give the model 2 tools, a weather lookup and a calculator, and ask a compound question, the weather in Paris in Celsius, and what is 47 times 19? The model correctly emits both function calls as XML in a single turn. Our parser turns that XML into structured calls. We execute the real Python functions, which return 18 degrees and 893, and we feed those results back. The model then composes a clean final answer that combines both. The entire round trip, including 2 generations, completes in about 3/4 of a second. Use case 3 tests code generation, and we hold it to a high bar. We don't just look at the code, we run it. We ask the model to write a function that converts a Roman numeral to an integer. It produces a correct implementation that properly handles subtractive notation, like 4 and 9. We then extract that code, execute it untouched in a fresh namespace, and run it against 6 test vectors ranging from 3 up to 1994. The model's own code passes all 6 in just over a second. A 1 billion parameter model wrote working, tested code on the first try. Use case 4 showcases the model's fast, assistant face. With think mode turned off, we fire 5 short questions: a capital city, a 1-sentence science explanation, an authorship question, a French translation, and a request for 3 bullet points. Every answer is correct, concise, and immediate. The model sustains around 130 tokens per second, with a mean latency well under a second. The shortest answer, the French translation, came back in about 0.06 of a second. This is the low latency experience that makes a small on-device model feel genuinely responsive in a real application. Let's pull the performance picture together. Across all 4 use cases, the model loaded in about a second and occupied only around 2 GB of video memory, leaving the 24 GB 4090 almost entirely free. It generated steadily at 120 to 146 tokens per second, delivered sub-second answers in fast mode, and most importantly, it was correct, the right math answer, working code, accurate tool calls, and solid knowledge responses. That combination of small, fast, and correct is the whole point of an on-device model. So, what should you walk away with? 4 things. First, the standard Llama architecture means 0 integration friction. If your stack runs Llama, it runs this. Second, 1 checkpoint flips between a fast assistant and a careful reasoner with a single flag, so you don't manage 2 models. Third, real agentic tool use works in plain transformers, with a production path through SGLang when you need it. And fourth, this model punches well above its 1 billion parameter weight class, all on a single consumer GPU. Compact, capable, and practical, that's MiniCPM5-1B. That brings us to the end of the training. Thank you so much for watching. This tutorial, the code, and the narration were put together by Omar Hosni. The model itself, MiniCPM5-1B, is released by OpenBMB, and every result you saw was captured live on a single NVIDIA RTX 4090. I hope this gave you both the understanding and the practical confidence to put this remarkable little model to work in your own projects. Until next time.